In this video, we'll be looking at aqueous solutions, solubility rules, and writing molecular and complete ionic equations. So far, we've looked at balancing chemical equations so that we have the same amount of atoms on the reactant side as we do on the product side. We also noticed that when we were writing chemical equations, we would say what state that the compound was in. We would say an S for solid, an L for liquid, a G for gas, or we used AQ for aqueous. In an aqueous solution, there is a substance that is dissolved in water, and we call this mixture a homogeneous mixture because you can't actually see the substance. There's no difference between the substance and the solution because the substance has been dissolved. So anything that's dissolved in water creates an aqueous solution. Not all compounds dissolve in water. Compounds that dissolve in water are called soluble, and compounds that don't dissolve in water are insoluble. When a compound dissolves in water, and it's an ionic compound, what happens is that the components of the compound dissociate into their positive and their negative ions. Let's look at an example of an ionic compound that dissolves in water. Table salt is an ionic compound that contains sodium and chlorine, which comes together to create sodium chloride. Sodium, which has the symbol Na, is a positive ion, known as a cation, and is the metal ion, and chlorine is the non-metal ion, and it is negative. It's the anion. Here you can see that sodium and chlorine have disassociated from each other when they're dissolved in a solution. So this would be an aqueous solution of sodium chloride. Substances such as sodium chloride that completely disassociate into their positive and their negative ions create a solution called a strong electrolyte. Electrolytes, such as dissolved sodium chloride in water, are able to conduct electricity. Fun fact, distilled water, which does not contain any dissolved compounds, will not conduct electricity. It is the dissolved compounds in water that causes water to conduct electricity. So if you were to fill up a bathtub with distilled water that has not touched any ionic compounds, it would not conduct electricity. Of course, as soon as you step into the bathtub, the salt on our bodies does dissolve into the water, and that will create an electrolyte solution. Let's look at another example of an ionic compound that dissolves in water to make an aqueous solution. Here we have silver nitrate, and silver nitrate contains positive silver ions, and that's the metal part of this ionic compound. And then the nitrate is the polyatomic ion, and it is the negative ion. So you can have ionic compounds that contain polyatomic ions, and when they dissociate in water, you can see that the silver and the nitrate dissociate, and the nitrate dissociates, but it stays in a complete unit. So the nitrogen and the oxygen inside the nitrate do not dissociate. Just the polyatomic ion, that negative polyatomic ion of nitrate, dissociates from the positive silver ion, and then that's where they get soluble and they dissolve. So it's important to remember that when compounds containing polyatomic ions, such as nitrate in this example, dissolve, the polyatomic ions dissolve as intact units. It's very important to note that not all ionic compounds dissolve in water. So looking at this example, we have silver chloride. So silver is the positive metallic ion, and chlorine is the negative nonmetal. And together, they create silver chloride. And silver chloride is an ionic compound containing a positive and a negative ion. But when you add silver chloride to water, it does not dissolve. It does not dissolve, and the silver chloride remains as a solid within the liquid water. It does not dissociate into positive silver ions and negative chlorine ions, so it doesn't dissolve. This means that we can say that silver chloride is insoluble. So even though it's an ionic compound, it's not soluble in water. It will not dissolve. So how do you decide whether an ionic compound is going to dissolve in water and create an aqueous solution, or whether it is going to be insoluble and not dissolve? Well, on table 7.2 on page 217 in your textbook, we have the solubility rules, and the solubility rules are going to help us decide whether an ionic compound dissolves in water to make an aqueous solution, or whether it's insoluble and therefore stays as a solid in water. You can see that the table is divided into two groups. We have compounds containing ions that are mostly soluble, and compounds containing the following ions which are mostly insoluble. So our soluble compounds are going to create an aqueous solution, and our insoluble compounds are going to be ones that, when we put it in water, are going to remain as a solid. Let's look at the compounds that are mostly soluble. A compound that is soluble is going to dissolve in water, and compounds that contain these positive ions, lithium, sodium, potassium, and ammonium, are going to be mostly soluble. For our negative ions, we have nitrate, C2H3O2, chlorine, bromine, iodine, and SO4. But notice that there are exceptions, that just because you have these ions in the compound, there are exceptions. So we're going to have to look at the exceptions to really decide whether something's soluble or not. Insoluble compounds contain OH and S, or CO3, PO4, but again, there are going to be exceptions to these rules. So let me show you how to use the solubility table to decide if something is soluble or insoluble. Let's look at some examples of ionic compounds and see if we can identify whether they are soluble or insoluble based on the ions that they contain. Our first example is silver bromide. So we have silver is our positive ion and bromine is our negative ion. The first thing I want to do is see if either the silver or the bromine is found in either of these soluble or insoluble groups. And I can see that I do have bromine right here listed as being mostly soluble. Next thing I'm going to do is look across and see if there's any exceptions. So with bromine as my negative ion, it looks like it's going to be a soluble compound. And then looking over at the exceptions, it says when any of these ions pair with silver being one of them, the compound is insoluble. So even though we have bromine, which would make the compound soluble, silver is an exception right here. So that means that this one is going to be insoluble. So I'm just going to put INS for insoluble. Let's look at our next ionic compound. We have calcium and chlorine. So calcium chloride. Calcium is the positive ion. Chlorine is going to be the negative ion. First thing is I'm going to see if I can identify either of those in this group or this group, and I can see that chlorine is listed as being soluble. So then I'm going to go over and look in my exceptions list and see if calcium is an exception. And I can see that I have silver, mercury, and lead are the only exceptions to this. So this is going to mean that calcium chloride is going to be soluble. Next one, I have lead and nitrate. Lead is my positive ion. Nitrate is my negative polyatomic ion. I'm going to look for those in either of these two groups, and I see that NO3 is listed right here. So NO3 is soluble, and there are no exceptions to this rule. So this means that lead nitrate is soluble. Next we have lead sulfate, and we can see that sulfate is listed here as being soluble, but it does have exceptions, and lead is one of the exceptions where even though you have the sulfate to make it soluble, if it's paired with lead, it's going to be insoluble because it's listed in this exceptions list. So lead sulfate is going to be insoluble. Next one up is copper sulfide. Looking for copper and looking for sulfide, we can see that the sulfur is listed as being insoluble. And now we need to go over and look and see if there are any exceptions. We want to see if copper is an exception to this. So lithium, sodium, potassium, ammonium are exceptions, and also calcium, strontium, and barium are also examples of this as well. So but copper isn't listed, so that means that copper sulfide remains insoluble. Next up, we have iron and sulfate. We have sulfate listed here as being soluble, and looking across at the exceptions, iron is not an exception, so that means that iron sulfate is soluble. Next one, we have PbCO3, and CO3 is listed here as being insoluble, and lead does not show up in the exception rules, so this lead CO3 remains insoluble. And lastly, we have ammonium chloride, and ammonium chloride is listed here as being soluble, and there are no exceptions, so we're going to leave this as soluble. So you will need to use the solubility rules in Table 7.2 on page 217 to identify whether an ionic compound is insoluble or soluble. And again, you're going to look for your ions in this list or this list, and then always refer to the exceptions to see if there are exceptions to that rule. The application for solubility rules in chemistry applies to precipitation reactions and predicting what will be the product in a precipitation reaction. So first of all, let's talk about what a precipitation reaction is. The example that we have here is when you have potassium iodide, which you can see here is being dropped into a flask, and it is a clear, transparent liquid, and that's the potassium iodide, and it is being dropped into lead nitrate. And the lead nitrate is also aqueous. It's also this clear solution inside of the flask. So we have two aqueous solutions coming together, and when they come together, they create, so here we have these are the reactants. We have potassium iodide and lead nitrate, and you can see that they're both aqueous, so they're both solutions where those ionic compounds are dissolved inside, and that means that each of the ions are going to disassociate. So the potassium disassociates from the iodine, and the lead disassociates from the nitrate polyatomic ion. When they come together, they react. So we have a chemical reaction, and in that chemical reaction you can see that we have two products. So these ionic compounds rearrange, and the lead from the lead nitrate combines with the iodine from the potassium iodide, and this lead iodide is a new substance that precipitates. It's a solid. It's that yellow solid that's forming in the flask. So this is a precipitate. Ooh. So the lead iodide becomes the precipitate, which is that yellow solid that's forming in the flask. And then the other product is this potassium nitrate, and it remains aqueous. Now, when you are given just the reactants, you will be able to identify the compounds and what the precipitate will be in the product. So let's look at an example where we are given the reactants and we're asked to create the products. So first of all, we have sodium carbonate, which is written as Na2. The subscripts here aren't written correctly, so I'm going to redo that. And then the carbonate, which is CO3. And we also have, and that's going to be an aqueous solution. And we're mixing it with copper 2 chloride. So that's going to be CuCl2, and that's also going to be an aqueous solution. And because they're aqueous, we know that in order to be aqueous, sodium carbonate has to dissolve in water, and also copper chloride also dissolves in water, or else we wouldn't have that they were aqueous after those terms. Now, when we mix these two ionic compounds, what's going to happen is that sodium has a positive charge and copper has a positive charge. CO3 is going to be your negative ion, and chlorine is also going to be your negative ion. So I like to put my charges. Sodium has a charge of +1, carbonate has a charge of -2, copper has a charge of +2, and chlorine has a charge of -1. Now when they come together, the sodium is going to come together with, because it's positive, with the negative ion from the copper chloride. So I'm going to put those together. So I'm going to have sodium and chlorine, and I know sodium is +1 and chlorine is -1. And then I'm going to combine that with the copper and the carbonate, CO3. And I know that my copper has a charge of +2, and carbonate also has a charge of, -2, so they're going to come together in a 1-to-1 fashion, just as NaCl comes together in a 1-to-1 fashion as well. So you want to make sure that you recheck your subscripts afterwards and see if you need to rearrange these now that they have come together. Once you've created your new compounds by taking the positive ion from one compound and combining it with the negative ion from the other compound to create your products, you now need to balance the equation. So I'm going to go ahead and balance my equation. I see that I have 2 sodiums on the reactant side and I have 1 sodium on the product side. I have 1 copper on the reactant side, 1 copper on the product side. I have 2 chlorines on the reactant side, and I have 1 chlorine on the product side. And then for my carbonate, I have 1 on my reactant side, and I have also 1 on my product side. So in order to balance this out, I can see that I need to balance out my sodiums and my chlorines. So I'm going to put a 2 here. That's going to give me 2 sodiums and 2 chlorines, and now everything is balanced out. So just by adding that 2, I'm now okay. And now the last thing I need to do in writing this equation is to find out if my sodium chlorine or my copper carbonate, either one of these are insoluble, because that's going to tell me that I have a precipitate, that a solid is going to form. So let's look at NaCl first. So I'm going to just scroll down here and look up NaCl. Cl shows up on my soluble list, and looking across to see if there's any exceptions, I can see that Na is not an exception. Therefore, NaCl is going to be soluble, which we know because NaCl is table salt and it is dissolvable. You can dissolve it in water. So I'm going to put the AQ after NaCl, so that's going to remain aqueous. The question is copper carbonate, is that going to be soluble or insoluble? And if it's insoluble, that's going to tell us that it doesn't dissolve, it's not aqueous, and it's going to become a solid, and that's going to form our precipitate. But first we have to make sure that. So I'm going to go back down to my solubility rules, and I see that CO3 is showing up as insoluble, and copper is not an exception. So that means that copper carbonate, let's move up here. There we go. Copper carbonate, it is going to be insoluble, and therefore it's going to be the precipitate in this reaction. So when we combine our sodium carbonate with copper chloride, we are going to form two new compounds. That's going to be calcium chloride and copper carbonate, and it's the copper carbonate that is insoluble and therefore is a solid in the solution, and this will be our precipitate. Okay, let's look at another example. Here we have lithium and nitrate. So lithium nitrate, which is an aqueous solution. So lithium nitrate is dissolved in water. And then we have sodium and sulfate, and that also is dissolved in water and aqueous. And we can see that they recombine. The lithium recombines with the sulfate, and the sodium recombines with the nitrate. So we have sodium nitrate and lithium sulfate that is created from this chemical reaction. The question is, does a precipitate form? And if we want to know if a precipitate forms, we want to decide if the products are soluble or insoluble. So let's look at each one. We have sodium nitrate. We're going to look for sodium and nitrate in our group here, and we see that the nitrate is listed here as being mostly soluble and that there are no exceptions. So that means that we can say that sodium nitrate is soluble, which means it will dissolve in water and therefore it's an aqueous product. Now let's look at lithium sulfate. We can see that lithium is also listed in the soluble side, and there are no exceptions to that. So that means that the lithium sulfate is also soluble and it's going to be aqueous as well. If you have two products that are aqueous, then this is not a precipitate reaction. So no precipitate forms in this case. In order to have a precipitate, you have to have a solid being formed. Here is our next example. We have lead and acetate coming together to create lead acetate. Lead is the positive ion and acetate is the negative ion. And it is reacting with sodium sulfate. And both of these compounds are aqueous. They're going to react with each other to create lead sulfate. So the positive ion from lead acetate, which is the lead, is going to combine with the sulfate, which is the negative ion from the second compound. And then the sodium ion is going to combine with the acetate. So we're just recombining the ions. What we want to know is whether a precipitate is formed. So we need to take each of the products and decide if they're soluble or insoluble. Let's look at lead sulfate first. Sulfate is listed in the soluble table, but lead is an exception to this. So that means that lead sulfate is going to be insoluble. And when it's insoluble, that means that it's going to form a precipitate. And then the sodium acetate, we can look for it, and we see that sodium is listed here as being soluble, and there are no exceptions to that rule, so sodium acetate is an aqueous solution. So that means that the lead sulfate is going to precipitate out as a solid in this reaction. Lastly, what I want to show you is different ways to write equations. At this point, we are very familiar with writing full equations called molecular equations. So a molecular equation is an equation showing the complete neutral formulas for every compound in the reaction. So here we have silver nitrate in aqueous form combining with sodium chloride, also in aqueous form. And those two reactants create silver chloride, which is the precipitate, and sodium nitrate, which is going to be soluble and therefore aqueous. So the silver chloride is going to be the solid, it's insoluble, and it is the precipitate. So when writing a molecular equation, you want to make sure that your ionic compounds are intact, that they're balanced, and also that you include whether they're aqueous, solid, liquid, or a gas in the equation. The next type of equation is called a complete ionic equation. And in complete ionic equations, you take each of the ionic compounds and you disassociate the positive ion from the negative ion and keep the type or the state of the ion with the ion. So if you have silver nitrate and it's aqueous, then you separate the silver, it remains aqueous. You separate the nitrate and it remains aqueous. And you do that for all the compounds. So sodium chloride, the positive sodium ion, aqueous, the negative chlorine ion, aqueous. For silver chloride, that's a solid and it's insoluble, and in complete ionic equations you're going to keep that compound together. We will only separate our soluble, our aqueous compounds. So where silver chloride is a solid and it's insoluble, it stays together in a complete ionic equation. And then our sodium nitrate, it is aqueous, so we're going to disassociate its ions to show that it's dissolving. So we'll have sodium aqueous and our nitrate, which is also aqueous. So far we have gone from the molecular equation, which is the complete equation where the ionic compounds stick together. Then we move to complete ionic equations where we separate all of the soluble compounds into their positive and negative ions, but we kept the insoluble compound together. Now we're going to move into net ionic equations. And net ionic equations only shows the species that actually participate in the precipitate reaction. So what we're going to do is, and we're missing an arrow here, there should be an arrow, you can see that we take our insoluble compound and we write it as the intact product. And then we're going to look for the ions that are involved in that precipitate. And we see that's going to be our chlorine ion and our silver ion. And we're only going to bring those down into the net ionic equation because those are the species, those are the elements, those are the ions that actually participate in this reaction. So remember, when writing complete ionic equations and net ionic equations, we are only separating aqueous ionic compounds into their constituent ions. We do not separate solids, liquids, or gaseous compounds because those are insoluble and remain together. So let's look at an example of taking a molecular equation, writing the complete ionic equation, and then writing the net ionic equation. So what we have here is we have hydrogen bromide with calcium hydroxide as being the reactants, and these are both aqueous solutions. They react together to create water, which is in the liquid form, and calcium bromide, which is aqueous. And this is the complete molecular equation, and it also has been balanced, so we don't need to do anything more with this equation. The first thing that I want to do is write the complete ionic equation from this. And whenever you're writing a complete ionic equation, you want to take all of the aqueous compounds and separate them into their positive and negative ions. Anything that is written as a liquid, solid, or gas is the precipitate, and we're going to leave that compound intact. So because the water is insoluble, when I write the ionic equation for this, I'm going to keep that together because that is considered our insoluble precipitate. Everything else is soluble, so we're going to separate them into their positive and negative ions. So looking at hydrogen bromide, hydrogen is the positive ion and bromine is the negative ion. So I'm going to take the hydrogen out, and you can see that I'm going to bring down the coefficient for the hydrogen, and that's aqueous, plus the bromine, and again there's 2 bromine, so I need to bring down that 2 again, and that's aqueous. And now I've taken care of the positive hydrogen ion and the negative bromine ion from hydrogen bromide. Next, I'm going to add my positive calcium ion, which is aqueous. Oh, and I've run out of room. Plus my hydroxide ion, which is negative. There we go, and that's going to be aqueous. So you'll notice that if you have a coefficient, it's going to apply to both the positive and the negative ion, so you want to make sure that you write it down for each the positive and the negative ion. You want to include the aqueous designation for all of the positive and negative ions for that reaction. Now on the product side, I've already kept my water together, but now I want to include my calcium, which is my positive ion, aqueous, plus, bring this over a little bit, my bromine ion, which is negative, and that's going to be aqueous, and I've added that as well. So, oops. And there I have my complete ionic equation where all of my soluble ions have been separated or disassociated. I've included coefficients where needed and also all of my aqueous, but I've kept my insoluble compound together, my H2O. My last step is going to be my net ionic equation. And the net ionic equation is always going to be the insoluble compound, which in this case is water, and then it's going to be the ions that make that up. And the ions that make up that water are going to be my hydrogen and my hydroxide. So I'm going to bring those down to H plus aqueous plus my OH2 aqueous, which is going to be the negative. And that comes together to create my 2 H2Os, and this is my net ionic equation because I'm just showing those ions that participate in the creating the precipitate. Participate in creating the precipitate. Let's go through this again with a new example. So in this example, I have lead nitrate, which is aqueous and soluble, combining with lithium chloride, which is also aqueous and soluble, and they recombine to create lead chloride, which is the solid and the precipitate, and also lithium nitrate, which is aqueous and it's soluble. So this is the complete molecular equation, and you can see that it has also already been balanced, so we don't have to balance it. Now to make the complete ionic equation, we're going to separate all of the soluble compounds, and we're going to keep the precipitate together, which in this case is going to be the lead chloride because it's designated as being the solid. So we're going to write our Pb separately because that's our positive ion, plus our negative ion, which is NO3 and that's going to be our negative ion, aqueous, plus 2 Li, and we have a charge of positive for the lithium, and that's aqueous, plus our chlorine, which is also 2, and it has a negative charge, and that's aqueous. So that's our reactant side. And now I'm going to take my product side. I'm going to keep together my lead chloride because it's the precipitate and it's solid, but I'm going to separate my lithium from my NO3. There we go. Because my NO3 is going to be disassociate from my lithium, and you can see that because there's a 2 in front of the lithium nitrate, I also want to make sure there's a 2 in front of my lithium and a 2 in front of my nitrate. Now I'm going to go ahead and do my net ionic equation, and my net ionic equation is going to just have my lead chloride as my product because that's the precipitate, and the ions that participate in this are going to be my positive lead ion and my negative chlorine ion, which is right here, and there's a 2 in front, so I need to make sure I keep that, and it's going to be 2 chlorine, which is negative and aqueous. So this is going to be my new net ionic equation where I just write down the ions that are involved in making the precipitate, and I just want to copy them exactly as I have them in my complete ionic equation. So the final words on creating complete ionic equations and net ionic equations. You always want to disassociate the positive and negative ions from the soluble compounds and keep the insoluble compounds together. You also want to bring your subscripts down, they won't change, and you also want to bring any coefficients down and make sure you apply them to both the positive and the negative ion. In terms of what the charge is, you're going to have to go back to when we did figure out charges from the periodic table, and you can tell what charge it is from what group they are in, so you can include that as well. So don't forget your charges. Don't forget to disassociate your soluble compounds. Make sure that you bring down all the subscripts and that you apply the coefficients to both the positive and the negative ions, and you will write a correct net ionic equation formula. These take a little bit of practice, so make sure you do a lot of practice. There are a bunch of examples in your textbook that you can do to practice this skill. Well, that's it for this video, and I thank you for watching. Bye for now.